In the previous video, we got up to the point where we found the recurrence relation to, or at least the form of a recurrence relation to our differential equation. We also found that the two initial roots were R1 is 1 and R2 is a half. And what we're going to do is we're going to substitute those back in, and we're going to get two recurrence relations. Generally we will. All right, now in this case, something strange is going to happen because it's an easier example. So let's start with where R1 is going to be equal to 1. So if we do that, we're going to get 2c sub n plus 1 times n. Right, so that's going to be n plus r minus 1, where that's going to be 1 minus 1 minus, and this should be c sub n, excuse me, not c sub 1. And then minus c, we're going to have n plus cn, and that should be n plus 1, excuse me. So this will be n plus 1, and that's going to be equal to 0. All right, now, how do we simplify this? Well, we can certainly factor out the cn, just like we did before, and then maybe some other stuff will simplify inside of there. So let's just factor out c sub n, and that's going to give us 2n squared plus 2n minus n minus 1 plus 1 equals 0. All right, by the way, all of this is for naught, because cn is going to be 2n squared plus n is equal to 0. All right, now we already said that c naught cannot be equal to 0. And right here, remember, n is the index, so n is going to be 1, 2, 3, 4, 5, etc. It's the index of the differential of the series. So this will never equal 0. In fact, the lowest number it's ever going to be, in this case, right, is going to be, when we plug in 1, that'll be 3. All right. So what does that tell us? All right. So since this will not be equal to 0, all right, that means that the only way this can be true is when c sub n is equal to 0. But c naught can't be equal to 0. So the only one that's going to be true is for c naught. Okay? So basically, let's hold on to this. And our solution, remember we plugged in 0 before? And so now we can say that at least when r is equal to 1. So let's make that apparent. Okay, so when r equals 1, the only valid solution is when n equals 0. And again, that's because of this right here. All right? And so what does that give us? Well, that gives us c naught. And remember, it's going to be x minus 1 to the n plus r. Right? Or that's just going to be 0 plus 1, so that's going to be c naught x minus 1 to the first power. And that's one of our solutions. Right? Now let's get the other solution. Okay, so that's the one where r is going to be a half. Right? So this one was the one where r was equal to 1, or r1. So now we're going to have r sub 2 is equal to a half. And let's just substitute that back in. And remember, we have this equation, or at least this setup that we have. So I'm going to move this down again, so that way we don't I don't make any copy errors. And so when r is equal to a half, all right, this is going to be a little bit uglier, but that's okay. So that's going to give us 2c sub n times n plus a half, and then n plus a half minus 1, minus c sub n, n plus a half, and then finally plus cn is equal to 0. You could pretty much imagine the same thing is going to happen as it did before. All right, so we're going to factor out the cn, and that's going to give us 2 n plus a half, n minus a half, minus n plus a half plus 1. All right, now a sneaky trick, we can factor this 2 in here to make this a little bit easier on ourselves. By the way, this should be equal to 0. So c sub n is going to be equal to 2n plus 1, and then n minus a half minus n plus a half plus 1. All right, and almost there. So c sub n is going to be, just FOIL this out, 2n squared minus n plus n minus a half minus n minus a half plus 1. Some good news. Negative half, and 1, minus n plus n. So that's going to go away. So what do we get? We get 2n, that should be a square, 2n squared, and it looks like we're going to have a minus n is equal to 0. Right? And when is this true? Well, either when Cn is equal to 0 or when n is equal to 0, right? Now remember, that's the only cases that can be true. So when n equals 1, 2, 3, 4, 5, we can't have that, all right? Otherwise, then this is not necessarily going to be true. And that means that C1, C2, C3, C4, etc. are all going to be equal to 0 as well. The only one that cannot be equal to 0 is C0. All right, so given all that, when n is equal to 0 and R2 is equal to a half, right, that means that the solution we get is that y is going to be equal to C sub naught x minus 1 to the 0 plus a half, right? So it's n plus r, or in other words, that's going to be C naught x minus 1 to the 1/2. Right? And finally, what we can do is we can get a linear combination of these values. So this is our second solution. So I'm going to call that y2, and up here I'm going to call this one y1. We got a solution earlier. I can't find it. I must have lost it somewhere. Yep, it's right here. So this is going to be our y1. And so finally, the entire solution is just going to be a linear combination of those two. So remember, we can say that y at x is going to be equal to y1 plus y2. We're not going to use C0. We're going to use something like B0 instead. So that's going to be equal to, let's just use C0 for the first one. So that was our C0, x minus 1 to the first power, and then plus, let's just call it B0, x minus 1 to the 1/2 power. All right? And that's the total solution that we get to our differential. Now this was a very easy example, and notice when I say easy, it was easy because of all this mess right here when n just canceled out after 0, right? In the next example, we're going to see that that's not going to happen, and we're going to have to get two recurrence relations. All right, so hang tight for that one, but hopefully this gives you a good understanding of the method of Frobenius, and that it was, by the way, a case 1. I think I forgot to mention that. Remember, R1 was 1, R2 was a half, and clearly these do not differ by an integer, so not differ by an integer. All right, so that's why we had to use this case 1 all the way back up here. I did forget to mention that. All right, but remember, if they do not differ by an integer, then we just go through and we use the two cases that we're normally accustomed to. All right, so hopefully that makes sense to everybody. If you want to check the solution to make sure that it indeed does satisfy the differential, just find a couple derivatives and then slap them back into the original differential and see if it works. All right. In the next example, we're going to see what happens when we get one of those recurrence relations, and we're not going to have that n1, n2, n3 is going to be equal to 0.